In this video, we're going to go ahead and talk about the Euler product formula. Now, I know it's not necessarily calculus related, but the Euler product property is something that has been fascinating me for the past week. And it's mostly because I got my hands on the journal that Euler wrote back in 1744. And there's nothing like reading something that the greatest mathematician of all time put together. Now, the Euler product formula combines a nice harmonic series into something involving just the prime numbers. And that connection alone motivated Riemann 100 years later. Because Riemann combined this particular formula and there's other functions to find a better understanding of prime numbers. And if you heard of anything called the Riemann hypothesis, or if you truly just understand anything about prime numbers, then you're gonna appreciate this particular formula. This was the paper that Euler wrote back in 1744. Now, he wrote it in Latin, so it's a little difficult for us to understand, but in here he talks about how he was inspired by typical problems that he talked about with mathematicians like Goldbach. Now, there's so many theorems to look at, but he has theorem 8, which this is where he introduces what we call the Euler product formula. He starts off with the harmonic series, and at the end he shows this particular equation, which tells us this is the form for the harmonic series that we're going to talk about. You have a sum from 1 to infinity of 1 over n to the power of s. Now, Euler didn't write it this way, but he did introduce this sigma notation later on, so this is how we're going to keep it. But what does this mean? Let's just say we start off with 1. Well, we have 1 over 1 to the power of s, which is just 1 over 1. So I'm just gonna write that as 1. And now I'm gonna add the next term, which is gonna be n is equal to 2, which is gonna be 1 over 2 to the power of s. And you can continue this pattern by going plus 1 over 3 to the power of s, plus 1 over 4 to the power of s, plus 1 over 5 to the power of s, and this will just continue on to infinity. So what you're doing is you're finding a nice sum for every single number from 1 to infinity. So this will go on forever. But now look what happens when I multiply everything by 1 over 2s. This is our first prime number in 2. So what happens when I multiply everything by 1 over 2s? Well, what we're gonna have is 1 over 2s summation from 1 to infinity of 1 over n to the power of s is gonna equal to, well, you're gonna multiply the 1 times 1 over 2s, so this is 1 over 2s, plus, when you get to this portion right here, you're gonna have 1 over 4 to the power of s. And then when you do it to the 3, you have 1 over 6 to the power of s, and you have 1 over 8 to the power of s. And then when we get to this one, you have 1 over 10 to the power of s, and this will continue. Now, notice what happens here. You're basically accounting for all the denominators that have an even number. In this case, it's a multiple of 2. So what happens when I subtract the top function minus the bottom function? Well, what I will get is gonna be, let's go ahead and do 1 over 2 to the s summation from 1 to infinity of 1 over n to the s minus 1 over 2 to the s summation from 1 to infinity of 1 over n to the s. This looks like a 5, so I'm just gonna fix that. And now what's gonna happen when we subtract this minus this? Well, you have 1 minus, there's nothing to cancel out, so you really just have 1 plus. But now look this, or check this out. 1 over 2 to the power of s, this cancels out with this one. This will stay the same because there's no 1 over 3 to the power s in this second function, so we have 1 over 3 to the power of s. And now we continue. This 1 over 4 to the power of s will cancel out with this one, but there's nothing with a 5, so now we have 1 over 5 to the power of s. If we continue that process, every single value that has a denominator or an even denominator will cancel out. So what we're left with is 1 plus 1 over 3 to the s, plus 1 over 5 to the s, plus 1 over 7 to the s, plus 1 over 9 to the s, and I can just continue. And now if you notice, I have some prime numbers, but as we continue going forward, we're just gonna have all the odd values, 3, 5, 7, 9, and we have 11 and so on. I misspoke because 9 is not a prime number, but you can kind of see that we have some primes here, 3, 5, and 7. The next one will be 11. Okay, so just to kind of simplify this out, let me go ahead and factor out the 1 over 2s. And one thing that I should have written is that when I subtracted this top function over here, I did not have a 1 over 2 to the s. I kind of got that incorrect because I put the 1 over 2 to the s there on top. So I really just have this. But what happens if I factor out both of this summations from these two terms? Well, I will have the summation from 1 to infinity of 1 over n to the s, and then I really have times 1 minus 1 over 2 to the s. 1 plus 1 over 3 to the s, plus 1 over 5 to the s, plus 1 over 7 to the s, plus 1 over 9 to the s, and we continue. Okay, so now let's go ahead and try a different thing. Let's go ahead and multiply everything by 1 over 3 to the s, so the next prime number. So I have 1 over 3 to the s of this summation, which is this entire thing, 1 minus 1 over 2 to the s. And then when I do that, I'm gonna have 1 over 3 to the s plus this will become 1 over 9 to the s plus this will become 1 over 15 to the s. This will become 1 over 21 to the s, and then this will become 1 over 27 to the s, and we will continue. And now let's go ahead and subtract this minus this, and hopefully you would agree that I'm gonna have this right here. I'm gonna have 1 minus 1 over 3 to the s times this portion right here. So it's gonna be 1 minus 1 over 2 to the s. I just kind of move the summation around, so I have 1 to infinity of 1 over n to the s. Now what I'm gonna get here is, there's nothing to cancel out the 1, so we really just have 1 plus the 1 over 3 to the s cancels out with this 1 over 3 to the s. The 1 over 9 to the s cancels out with this one. So we're left with the 5 and the 7. So we have 1 over 5 to the s plus 1 over 7 to the s, and we will just continue and cancel out every multiple of 3 in the denominator. So this will leave us with 1 over 1 plus 1 over 5 to the s plus 1 over 7 to the s plus 1 over, the next one will be 11 to the s, 1 over 13 to the s, and this will continue. So as you're looking at this pattern, every single multiple of 2 got canceled out, every single multiple of 3 got canceled out, and then every single multiple of 5 will then cancel out, and then of 7, and then of 11 and 13, and we will continue that process on and on and on. So if we were to continue doing this, we will get an infinite summation or an infinite multiplication here that will look like this. So let's just say I start off with 5, and I have 1 minus 1 over 3 to the s, times 1 minus 1 over 2 to the s, and then we have this summation. And if we continue doing this, you will see that if I continue subtracting, the one thing that never cancels out is the 1. It didn't cancel out here, it didn't cancel out up here, so it's not gonna cancel out as we continue that process. So we're left with 1 here. And now what we're gonna do is we're gonna divide this entire thing to the other side. So that tells us that the harmonic series, the one that Euler was talking about, is equal to 1 over, and then it's this entire product for every prime number. So you have 2 to the s, 3 to the s, 5 to the s, 7 to the s, and so forth. This will become this summation, and we have 1 minus 1 over p to the s. And now we can just sort of like simplify this. So this will become the summation for all p primes, and this will be 1 over 1 minus p to the negative s, and we are done. Let me just go ahead and fix this parentheses, and guys, this is exactly what the Euler product formula is gonna be. Euler introduced this back in 1744, and almost 100 years later, Riemann found a nice connection with this formula and plugged it into a nice formula of his own to create a perfect understanding of the prime numbers. That's if he's correct. Fast forward 166 years to today, and we're still trying to solve this. We are starting with the Euler product formula, and now we're at the Riemann hypothesis, and mathematicians like Terence Tao are still trying to prove this, and hopefully in our lifetime, we can see the proof. But if there's anything that you're gonna take away from this video, is that you truly appreciate Euler's product formula. That's gonna do it for today, and I'll see you in the next one.